we're not going to read a lot from Hidden Harmonies, which is more a book for mulling over at leisure and letting your thoughts take off from its pictures. I did the pictures. We'll read enough to give you a sense of the great Pythagorean adventure, and then let's talk together about its pleasures and those of math in general, and also about the scary parts. So, I'll begin at the beginning. The Englishman looked down from the balcony of his villa outside Florence. Guido, the peasant's 6-year-old son, was scratching something on the paving stones with a burnt stick. He was inventing a proof of the Pythagorean Theorem. "Do just look at this, do," he coaxed and cajoled. "It's so beautiful and so easy." And Guido showed the Englishman's son how the same square could be filled with 4 copies of a right triangle and the squares on its sides, or the same 4 triangles and the square on the hypotenuse, so that the 2 squares of his first diagram must equal in area the square in the second. And the Englishman thought of the vast differences between human beings. We classify men by the color of their eyes and hair and the shape of their skulls. Would it not be more sensible to divide them up into intellectual species? There would be even wider gulfs between the extreme mental types than between a Bushman and a Scandinavian. This child, I thought, when he grows up, will be to me, intellectually, what a man is to a dog. And there are other men and women who are perhaps almost as dogs to me. But the child never grew up. He threw himself to his death in despair at being snatched from his family by a well-meaning signora who forced him to practice his scales and took away the Euclid that the kind Englishman had given him. A true story? Emphatically not. It's Aldous Huxley's Young Archimedes, published 3 years after Sir Thomas Heath's History of Greek Mathematics came out in 1921, with its quotation from ancient Callimachus: "By happy chance Bathocles' son found old Thales scraping the ground and drawing the figure discovered by Pythagoras." The falsity of this story isn't just in Huxley's having patched it together from what he had read in Heath and from the legend of the brutal centurion who, sent to fetch Archimedes, killed him instead because he wouldn't stop drawing his diagrams in the dirt. It is much more deeply false. False to the way mathematics is actually invented, and false to the universality of mind. It's certainly dramatic to picture superhumans in our midst, living put-downs to our little pretensions, yet testimony to more things in heaven and earth. But the actual truth has greater drama still, woven as it is of human curiosity, persistence, and ingenuity, with relapses into appeals to the extraterrestrial. This is the story we shall now tell.
The great thing about math is that you never have to take anyone's word for it. It's the only human undertaking founded on irrefutable proofs. Not surprising, then, that there aren't too many of these. Not too many foundations, not too many theorems, that is, statements that have proofs that someone or other came up with attached to them. So the Pythagorean theorem is especially astounding because it has several proofs. It has more than one proof. How many would you guess there are? Hundreds. Other guesses? Do I hear tens? Well, let me read from the book. Some people collect Ketchikan beer coasters, some Sturmey Archer 3-speed hubs, others wives and ailments. Jury Whipper collected proofs of the Pythagorean Theorem. He wasn't the first. 59 years before him, in 1821, Johann Joseph Ignatius Hoffmann published more than 30. In 1778, a Frenchman named Fauré included 38 among his Curiosités géométriques, and a Herr Gropp had translated others from a Russian anthologist. Nor was Jury Whipper the last. Professors Yanni and Calderhead from the universities of Worcester in Ohio and Curry in Pennsylvania gathered together some 100 proofs between 1896 and 1889. A lawyer at the District of Columbia Bar named Arthur Colburn published 108 of his own, starting in 1910. Perhaps the currents of litigation ran more slowly before air conditioning. On the shoulders of these giants still stands Elisha Scott Loomis, the boy born in a log cabin in 1852 who rose to be a 32nd degree Freemason and, quote, plowed habit formation grooves in the plastic brains of over 4,000 boys and girls and young men and women. He tells us that of all the honors conferred upon him, he prized the title of teacher more than any other, quote, either educational, social, or secret. Was he as leonine as his portrait shows him? Florid mustache and wing collar? You'll have to buy the book to see that. Or should we believe a penciled note in the Harvard Library's copy of his book? He was somewhat high in manner, but was in reality a good sport. I never met him. Then how did you know, G.W. Evans? Pythagorean investigations breed mystery. Here's another. How many proofs are there in Loomis's book? Be a Babylonian, you say, and count them. But counting, as even a Babylonian knew, is one of the hardest of human tasks. Loomis claims to have 367 proofs in his second edition, though some are circular, some defective, some no more than variations on or subsumed by others. Are the algebraic proofs, which he says readily follow from this or that geometric demonstration, to be thought of as different from them? He asks about a possible proof here, quote, can't calculate the number of others there, and speaks of several, a number of, and countless different proofs from those he gives. 9,728 proofs, for example, derive from his figures for algebraic proofs 6 and 7, he tells us, and 65,780 more from his figure 8. When he writes, as for his geometric proof 110, of more cases extant, does he mean more than he has given? Are two proofs really different if a square in one has no more than slid sideways from that in another, or if a grid of lines is differently parsed? We conclude that his book contains 367 proofs, minus a few, plus several, increased by a number derivable but not in fact derived, to which are added those that are other and different, resulting in many plus a multitude, increased by a limitless as well as an unlimited horde of the likely, and a slew indefinitely great that will be discovered by, he says, the ingenious resources and ideas of the mathematical investigator, giving us, as an approximate total, more than we should or could or may or want to count. This amplitude is consonant with the generous spirit of brotherhoods, Pythagorean or Masonic, and is an image of life itself. In the earth, below each tree of spreading order, the mice of somewhat gnaw, while chaos in its foliage is made by the insects of etc.
Loomis credits his 14th, such a small number, geometric proof to Miss E.A. Coolidge, a blind girl. He then gives us no more than a reference to the journal he found it in. What? Were his curiosity, his imagination, his compassion not stirred? Did his compulsion to move on to the next and the next and the next leave him no time to wonder at the visions of the blind? Not being in such a hurry, we hunted out the Journal of Education, volume 28, 1888, through the stacks in Harvard's Gutman Library, where it had, who knows how many years before, been misshelved, giving the diligent librarian a dusty 2 hours before she cornered it down a stack receding to infinity. "That made my day," she said. Terrifying view of life. And there, on page 17, was Miss Coolidge's proof, across from the notes and queries. What is the difference between Belfast in Chicago, Belfast in Maine, and Belfast in Ireland? What is the Aginian sect? Try Googling it. It's not there. Her proof, however, was not as it appears in Loomis, who had clearly exercised his editorial powers over it. He was somewhat high in manner. We give her original proof in the book with all its extraneous steps. What's particularly fascinating about this proof is that Miss Coolidge begins it geometrically, making and comparing shapes, but then turns to calculating with letters, when perhaps she can't quite figure out what's left and what's wanting. You might think that, being blind, Miss Coolidge would have resorted to abstraction as early as possible, but in fact she delays it as long as she can, trying to stay true to the spirit of geometry. Having followed her proof, if we now follow her, we may better understand the play between abstraction and different sorts of sensory information. But how find the woman behind Loomis's brief Miss E.A. Coolidge? It struck us that Coolidge is a good Boston name, and the journal in which her proof first appeared was published in Boston. Might she not then have been a student at the Perkins School for the Blind? We emailed Jan Seymour Ford, their research librarian, who answered that was inspired guesswork. Emma A. Coolidge was a Perkins student. She was born August 4th, 1857, in Sturbridge, Mass., and she lost her sight from whooping cough when she was a year old. She could only detect light and shadow, and none of the remedies her parents tried, having her wear gold earrings, putting talcum powder into her eyes, blistering her temple with poisoned flies, helped. After graduating from Perkins, she studied at Wellesley for a year, then returned as a teacher to Perkins, where one of her students is said to have been Annie Sullivan, later Helen Keller's tutor. Emma married, had a daughter, wrote children's books. Isn't this what we see in her proof? Or what you'll see in her proof if you look in the book where the proof is. Catching the chiaroscuro of prominent shapes, but navigating otherwise by those abstract relations with which practice and memory furnish the mind. What sort of imagination this involves may matter here. The blind mathematician Louis Antoine was led by his advisor Henri Lebesgue to study 2- and 3-dimensional topology because, quoting Lebesgue, in such a study, the eyes of the spirit and the habit of concentration will replace the lost vision. His equally outstanding compatriot, Bernard Morin, has been completely blind since age 6, was asked how he knew the correct sign in a long and difficult computation. By feeling the weight of the thing, he said. More tellingly, Morin distinguishes between what he calls time-like and space-like mathematical imagination, and surprisingly says that he excels at the latter. A problem with picturing geometrical objects is that we tend to see only their outsides, which hide what might be complicated within. Morin, who works with extremely intricate objects in 3 dimensions, has taught himself how to pass from outside to inside, from one room to another. Our spatial imagination, he says, is framed by manipulating objects. You act on objects with your hands, not with your eyes. So being outside or inside is something that's really connected with your actions on objects. Think of Emma sewing and knitting, or killing and dressing fowl. Might Emma's extraneous calculations have come from an intrusion of the time-like into her sounder, space-like imagination? And is the tactile yet one more intermediate between being and becoming?
So, spatial imagination. What does this mean? What does it mean when physicists talk of string theory and see these strings in 11-dimensional space? 11 or 9? Which is it? What does it mean when mathematicians toss around 12 and 200-dimensional space in their coffee-fueled conversations? They aren't superhuman. Like us, they can only see 3 dimensions. So let's go back 4 centuries together to look for an answer. This is from the book. In 17th century Ulm, the master reckoner Johannes Faulhaber discovered a spatial generalization of the Pythagorean Theorem and saw how it would lead him to a deeper understanding of 666, which he already knew was divine rather than diabolic. While the margins of our minds are too narrow to contain Faulhaber's Kabbalistic proof, we will unveil to you his rectilinear pyramid. Analogy, said his contemporary Johannes Kepler, is the greatest of my masters. Moving by analogy from squares on the lengths of a right triangle's sides to squares on the areas of a right pyramid's faces, he came up with this beautiful generalization. Given such a pyramid, 3 of its edges meeting at right angles, as in the corner of a room, the sum of the squared areas of these faces, A, B, and C, equals the square of the area on the last hypotenuse face, D. That is, A squared plus B squared plus C squared equals D squared. If not quite up there with 666, still pretty wonderful. In the winter of 1619, Descartes, passing through Ulm, may well have met Faulhaber. Local legend has it that one night, dazzled by Descartes' brilliance, Faulhaber reached out. I picture them as sitting on opposite sides of his fireplace in a stuffy, comfortable room with weather freezing outside. Faulhaber reached out and touched his guest to make sure that he was human and not an angel. Wouldn't you have done as much were your visitor to have mentioned that this theorem also held in 4 dimensions? So, enough of the book. Conversation. What do you make of that? What do you make of this talk of dimensions beyond those we can see? Is this meaningful? Is it meaningless? Is it a game? Is it the most important thing in the world? Any of the above? All or none? Or anything you'd like to talk about, whether it's the Pythagorean Theorem and its consequences, its applications, the still unsolved open problems in it? Is that a question, Rick? Yes.
I mean, I love that. The
Ah.
Or an optical illusion. I mean, how do you? Yeah, it looks like you can rearrange those triangles, and they fit in the square. But it just looks like you can do that.
So what is a proof? What constitutes a proof? Why are not the algebraic manipulations with letters and symbols and equal signs, why aren't those also an optical illusion or a linguistic illusion? Why aren't all proofs illusions? What isn't an illusion?
I think
that proof, I mean, I'm using my eyes.
Yeah.
Put it back. I'm not.
Yes.
Yeah. You're using your eyes
I'm
and
not thinking it through. I'm just looking at it. Yeah, there it is.
Yeah.
When I'm fiddling with X's and Y's, somehow I'm surer of it.
suppose instead of having just drawn, we had actually given you all four cutout triangles. We do this for classes. We figured the little tacky doing it for grown-ups.
We do it with 8-year-olds. So.
And so if you had, this is the big square, and you had these are the four triangles, all it takes is to take these two and put them here, and these two and put them there. And that really is the square on the short side.
But I see your point that here,
They seem to fit, but you know, there are various formulas in physics that are nearly correct.
Or like you
Not
can trisect
quite.
an angle.
Yep.
almost, as in origami.
Well, yeah.
Are you thinking of origami-like proofs for angle trisection or supposedly legitimate algebra?
In high school geometry, like
Ah, yes.
sort of trying to do various things, and our teacher encouraged you, well, try this, and maybe you'll trisect. So the level of resolution that you get, normal person drawing with
Yes.
brain.
And certainly the resolution you get cutting out pieces of construction paper is.
Right.
Yes.
And I've seen tricks where something is cut up and reassembled, there's a hole in it that wasn't there before.
There's a beautiful proof that 64 equals 65 if you take the right sort of rectangle apart and reassemble it.
Has to start with some earlier, theorems about congruences and the like, I remember.
There's a fascinating thing about visual proofs of the Pythagorean Theorem, of which there are thousands. The one that I find most startling in a mathematical sense is the Chinese got 3, 4, 5, and then said, well, that's it. That's true of all of them. Which seems to me a very unquestioning, and 3, 4, 5 is the only right triangle that they ever talk about, and that's the proof. And if you say,
But remember, there are cultural reasons behind it. At the time, this is 3rd century AD, at the time they said this, 3 and 4 were very important numbers. 3 was think of origami proof, or think of the proof of trisection of an angle. 3 was the circumference of a circle of radius 1, and 4 was the circumference of a square of side 1. So 3 and 4 are key numbers, and 5, well, 5 is my favorite number. So if it's true of that key mystical triangle, well, of course it's going to be true of other triangles. And there was another factor in the Chinese thinking about this, you'll see this in the book, that for them, the only triangle that had area was a right triangle, because you have height times length of base giving you area. Other triangles more or less had area. Rather like the problem with this 64 by 65 rectangle. But I think you've touched on a real nerve in mathematics. How does one validate a proof? Quis custodiet custodes ipsos? Who's in charge of the people in charge? What finally validates anything? In the century that's passed and the one that we're in the midst of, the foundational issues are devastating. Gödel seems to have proven that with mathematics, as we know it, there will be true statements that you cannot prove, and yet they're in some sense true. What does that mean? And when you take a proof which has all the paraphernalia of rigor attached to it, with equations and symbols reduced to definitions and axioms. Well, why take these axioms rather than those? A big issue with the Pythagorean theorem, where on surfaces other than a plane, analogs of the theorem hold, but not a squared plus b squared equals c squared. Perhaps something with cosines will hold instead on a sphere, or on an inverse sphere looking like well, how can one say what it looks like other than give you a picture? There.
Yeah.
On that, you get something with hyperbolic cosines, which is the equivalent of the Pythagorean theorem. So on which surface does the theorem hold? What does the mean?
I mean, we don't live on a plane, actually, and therefore the sort of shorthand way of describing what's going on is automatically not true.
What's marvelous about an evening like this is that we came here ostensibly to read to you, but actually we came here to find out things from you. And so we'd love to hear more of your ideas about what constitutes proof in mathematics.
It's been a while since I've taken it, but the basic idea was you start from something that you know, quote unquote, know to be true. So I can say that this is generally accepted, or this is true, and then you perform operations that you accept.
Yes.
Right. So a rotation in a plane, or you know, a mathematical manipulation to develop some new thing. And as long as you can say that I started from one place that I know to be true, and I performed operations that we accept to be correct or right, then the thing that I've come up with must therefore also be true.
It's nice that you have two parts to your story. One, you know the foundation, and you accept the way of developing from it. Two different kinds of.
The reason a little bit of the reason I hedge is that I've seen many fun experiments where you do the manipulation and you come up with a ridiculous result, like 64 equals 65,
yes.
Or there was something in the book about. But you basically can set 0 to equal to anything, because once you do enough manipulations, 1 equals 10 or 0 equals 100.
Galileo's patron, Guidobaldo del Monte, came to Galileo one day and said, I have a proof that God exists. Because God alone makes the universe, the one, out of nothing. And he was able to prove that 0 is equal to 1. And the proof is wonderful. In fact, you'll go home believers. 0 is equal to 1 minus 1 plus 1 minus 1 plus 1 minus 1 forever, right? That's 0. I'm just going to say again what came after the equal sign. 0 equals 1 minus plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. All I've done is just move parentheses around. But that equals 1. So 0 equals 1, so God exists. Now,
0 equals 1, so mathematics doesn't exist.
what was wrong there? The foundation seemed pretty secure. There is a 0, there is a 1, I think. There has to be a 0 because I wrote a book called The Nothing That Is. I don't know about the 1. But what about the accepted ways of moving from that? Can you reassociate sums? Well, the associative law of addition says you can. But the associative law of addition says you can for a finite sum. Not for an infinite series, though sometimes you can with a telescopic series. Sometimes it's legitimate. Actually, Ellen, you had a sentence which I think is relevant to what you were saying.
Which is about why, of all of mathematics, I feel the only thing I have any understanding of is geometry. And that geometry is the one open road into mathematics. You are seeing something, you are drawing something, it can be embodied, and you feel that you're much less likely to be duped than you are in the middle of a calculus proof where suddenly everything goes to zero and you're left saying, I guess, which is what I spend a lot of time in my math classes saying when people will say, isn't it obvious that? And you say, we know intuitively from our experience what is likely to be true in geometry. If you see this is bigger than that, you can look and you can measure and you can understand. And so we can stride confidently into trying to prove, because once you're convinced that something is true, you're amazing how much harder work you're willing to do than when you're not at all sure that what you're working on is in the right direction.
On the other hand, in contrast to that, this is a sentence from the book. A proof convinces us by showing that something apparently surprising or unlikely lies in a matrix of relations we recognize and truths we acknowledge, which I think is picking up several of the points made this evening. The fact that there are so many proofs of the Pythagorean theorem, doesn't that just by sheer, in a democracy, doesn't that make it truer? That there are so many different ways of coming at it, that it's just not some isolated fact with one thin thread of a proof to it. It's there, woven into our thought. In fact,
The text of Loomis.
yes, or take what Bernard Morin, the blind mathematician, said about the heft, the weight of the equation. He felt what the sign of it would have to be. And a late chapter in the book called The Deep Point of the Dream comes up, says, makes clear, I hope makes clear, this surprising truth that Euclidean geometry, the geometry of flat planes, which is distinguished from other geometries curved up in a sphere or like that strange shape, the geometry of the flat plane is based on one postulate, the parallel postulate, that through a point, not on a line, there is one, and only one, parallel to that line. That's the postulate which distinguishes our visual intuition and the geometry of flat planes, and it's equivalent to the Pythagorean theorem, which is quite astonishing. The two can be interchanged. Take away the parallel postulate, put in the Pythagorean theorem as your postulate, you'll get all of Euclidean geometry back. It's kind of amazing. Other issues you'd like to bring up? Yes?
Implicit in a lot of what you've been saying is that a lot of mathematical insight is a visual insight. And the question is, you've talked to a lot of mathematicians, do you think that they all think visually, or is there a sort of algebraic insight?
We have in the room with us one of the 10% of the mathematicians in the world who prefers the algebraic to the geometric. Is this not true, John? It's
Well, when you were saying that geometry, I was thinking, what about counting?
Counting.
Counting is so hard, though.
And ambiguous.
Think of Loomis. How many proofs in that book? Yeah.
You were easy.
If you have 10 fingers, you can go there.
But so based on what you're saying is, he is in a minority that there's, that most mathematicians think visually, or get derive their initial insight.
It seems to be true. I haven't read an authentic survey, but
Well, let's do sociology briefly. I mean, how many people found geometry more easy, comfortable than calculus?
yeah.
That's not a fair.
Okay. All right. Algebra.
Algebra? Well, there's nothing bad in algebra. I mean, there's nothing you have to take on faith in algebra. Calculus calculus, you begin to get this slimy.
Dividing by 0?
But I mean, calculus was invented in the 17th century. Let's compare two things that were invented
Okay.
relatively early.
Okay.
Invented.
You know, calculus is harder because it keeps so much.
You are claiming that both of these were invented.
I'm not claiming.
All right, so
No, but I do, let's then say algebra versus geometry.
make it arithmetic.
I feel safer when I buy myself with a geometry problem, more confident that I will be able to get through to something. Now, you say no. And the people who say no even more passionately than the people who say yes. And it's you know, how are you in the spatial brain may really be different.
The circle. Can we do the circle?
Yeah.
Yes.
Wanna do it again?
But this time, make it arithmetic, not even algebra. Arithmetic versus geometry.
With long division?
With long division.
That's what I
So how many now feel more comfortable with geometry than arithmetic? Ah, you were in fact a minority.
Geometry was all about, everything in geometry was proofs.
Whereas arithmetic, you're actually seeing the results of it, and they're confirmed by, 6 plus 7 is 7 plus 6. 6 times 7, which is harder, is 7 times 6. If you take a marching band, which is 6 rows of 7 high, and just rotate it 90 degrees, well, I just did something geometric, the 6 times 7 is still 7 times 6.
Usually, the basic theories of arithmetic like that were demonstrated geometrically.
Yeah, true.
I don't know
Yeah.
how else you would do it, that sort of.
They just shut up on it.
Yes. If you think of the axioms of arithmetic, the fundamental, the things we take for granted, commutivity, that it doesn't matter the order in which you add the numbers, or it doesn't matter how you associate them unless you have an infinite sum and are a patron of Galileo's. Those do ring with a deep truth, don't they? Beyond the visual. In fact, you can close your eyes and do arithmetic. So it has a deep ring of truth to it. I don't know. Perhaps that's the note to end on. We don't know. Yes.
Last Wednesday down in the basement here, we had our monthly philosophy group meeting, and the topic was truth versus the feeling of being right. Really being right is basically a book by Robert Burton, who's a neurologist, and his thesis is that not just the feeling of being right, but the feeling of knowing, I think he called it. The feeling of knowing is a physiological state that may have nothing to do with the external world or any kind of scientific proof or any kind of other kind of proof. And he makes a pretty good case, and I know nothing about mathematics, just about nothing. And when I look at the proofs, I go, how can anybody do this? I mean, like, this maybe is convincing to somebody, but that's pretty convincing. But beyond that, I think we're convinced by something, and I know not what it is, and politically as well as mathematically in every way, and it's much more to it than we're actually getting at.
Do you think the notion truth is an abstraction from the feeling of, how did you put it, the feeling of being right?
I think that philosophers have always sort of held a place for truth, as if there is such a thing. Robert Burton, this neurophysiologist, thinks that the feeling of knowing is what we actually work with. That guides our behavior, and it isn't based on proofs of any kind. It's just a feeling of knowing, and we can't resist it. We can't cause it to happen, and once it does happen, we can't resist it.
I have a very poor sense of direction. I feel I know how to get home from here. I'd probably make a lot of mistakes along the way, were Ellen not with me, but I feel I know it. It's just when I put it into practice that it begins to fall apart. But that a squared plus b squared equals c squared, when those are the sides and the hypotenuse of a right triangle, I can't unthink it. I can't make it not to be true, no matter where I am.
Even if you think of yourself as not being on a flat plane?
Ah, that's very hard to do. Although that's, of course, what I'm on, not a flat plane. Thanks very much for coming. We learned a lot.